Okay, I want to highlight a final problem of where the divergence theorem helps to evaluate surface integrals. So you can evaluate some flux integrals over a non-closed surface. So I'm emphasizing this because the divergence theorem does not apply to non-closed surfaces. And so let me just give you a concrete problem. So we're going to find the integral. I'm not writing it as a closed integral. It's going to be of f dot ds, where our force will look like zx, zy, z squared over 2. And here's the key thing. S is the top half of the sphere. X squared plus y squared plus z squared equals 1. And the top half is where this problem gets a little tricky. So notice the top half does not include the bottom half, and it also does not include the plane connecting these bottom points. We're literally just doing this top half, so it's not closed. So we cannot use the divergence theorem on S. But here's the thing. I'm going to put S alone. If we add an extra piece, then we can use the divergence theorem. So the trick is to close the surface. And you can do, and for these kinds of problems, you're going to do it in a way where the extra piece is easy. Where the extra piece has an easy integral. So I'm going to choose the z equals 0 and x squared plus y squared less than or equal to 1 standard unit circle. So in other words, I'm choosing the green piece. And the reason is because I want to use the z equals 0 property. Because what happens to f if I plug in z equals 0? If I plug in z equal to 0, look what happens. 0, 0, 0. So therefore, the integral over the z equals 0 piece is just 0. Right? So let me now show how to close that surface. If I take the surface integral over the top half and I add the surface integral over that bottom piece, we get the surface integral over that hemisphere, closed hemisphere. And so now this is closed. And so this is, and I'm also going to emphasize, this is what we want. The first integral is what we want. And the second integral is easy. And this is 0. And for this final piece, we're going to use the divergence theorem. So we're expressing what we want in terms of an easy piece plus a divergence theorem, which will also hopefully be easy. So because we've shown our easy piece is 0, we conclude our integral is equal to the integral over a closed surface. So I'm just going to indicate it like so, as an abbreviation. You know what I mean, of f dot ds. So now let's apply the divergence theorem. And now we're going to be integrating the inside of that surface. So let's compute the divergence. Let's hope it simplifies. For these problems, it will always simplify. Zx, zy, z squared over 2. So the divergence, so we have partial x of zx, partial y of zy, if I'm taking that dot product, partial z of z squared over 2. It looks like we just get z plus z plus z. So we have to do this integral, and this integral is pretty straightforward if you use spherical coordinates. Right, because if we do spherical coordinates, and if I remember what these are, using my standard RZ diagram, then we know that sphere, the hemisphere, it corresponds to phi equal to pi over 2. That's the maximum range. So phi will range from 0 to pi over 2. Theta, well, it's a sphere. It'll just go, there's nothing stopping this. There's nothing stopping the polar, the azimuthal angle, the theta angle. That'll just have its maximum range. It's cylindrical. And then finally, rho, it'll just go from 0 to 1. Because all the points on the inside are okay. That's the rho equals 0 parts. And all the points on the outside are also okay. So you just do an integral with these limits. And you also need, of course, that dv is the usual rho squared sine phi, d rho, d theta, d phi. Okay? And this integral is quite easy because you also just plug in z equal to, we'll use this diagram, it's just rho cosine phi. And so you just end up with a really easy trigonometric integral. So notice how our job actually got quite a bit simpler than having to integrate this nasty quadratic over a surface. I hope this was helpful. Thanks for watching.